What I have is a online software program called My Solar System. And if you just Google what you see up here in my search bar, it'll come up to it if you want to play around with it on your own. And we are going to use this to make some predictions and build some different systems using the force of gravity. And so we can see we have a satellite going in a circular orbit about a planet, or maybe it's a planet going around a star, it doesn't really matter. The yellow thing, the thing in the middle, has a mass of 500. The other thing has a tiny mass, so its gravity doesn't really affect the body one. Now, you guys know from Newton's third law, the force of gravity of the big guy on the little guy is equal to the force of gravity of the little guy on the big guy. But we're going to say big M is much bigger than little m. So that means the acceleration caused by the force of gravity on big M is negligible. And we won't always have this assumption. In AP Physics B, you always use this assumption. So later we'll look at what happens if we don't make this assumption. Well, I will say I am keeping an eye on the chat screen. I do have you muted because sometimes it causes feedback. And so if you do have a question or something, send a chat and I'll keep an eye on it and try and respond in a timely manner. So also notice we have the x position of the small mass is 200. That means this distance is 200. Now you might say 200 watts, same with the mass. Well, this software program uses different units than kilograms, meters, and seconds. So I'm not going to really worry about the units as we go through here. And so maybe that bothers you. Usually it's not a problem with this particular simulation. And then we also know how fast it's going. It's going 158 whatever units, and that's a constant speed. It's maybe looking a little jerky because of the some of the running the webinar software, but it's going to constant speed. What I want to know is, in the units of this program, what is big G? It's not 6.67 times 10 to the minus 11th. If you have the handout, I am on activity 3. And so I've skipped ahead. You may want to try the other ones that lead up to this later. I think you'll get something out of it, but we're going to jump right into 3. So what I'm going to do is draw a free body diagram of little m when it's right here. And so here is little m. And I'm going to draw and label all the forces on it. Well, when it's here, I know there's this one force, force of gravity, but I don't write mg, right? I write f sub g. And I want to indicate my coordinate system, and I always put one axis in the direction of the acceleration, or almost always. And that would be toward the center, right? This is just circular motion. And so this is the easiest free body diagram that you could do. And so we write Newton's second law, sum of the forces equal ma, and there's this one force, force of gravity, and that equals the mass. Which mass are we talking about? That's going to be important. When you draw a free body diagram and write F equals ma, this is the mass of the thing you drew the free body diagram of. And so it is little m here. I'm going to call body 1 big M and body 2 little m. And so the other important thing is this is a centripetal acceleration, right? It's going to constant speed, or it should be. It's, again, jerky because I'm running the webinar software. And so we have an equation for that, 2 equations really, v squared over r. And in mechanics C, there's another one. The linear speed is the angular speed times the radius. So if you substitute that in, you get omega squared r squared over r. So you get omega squared r. This can be real handy, and we'll use that later on another problem. But since we have the linear speed, this is v here, we know v is 158. Let's use v squared over r. So we put that into there. And then we have an equation for the force of gravity. It's g times the product of the masses over r squared. And so that's going to go into here. Now, if you are in AP Physics B, you probably have done all this. What's different about Mechanics C is you need to be able to derive these equations and do this all on your own. They'll just say, prove the result we're about to get here. So when I reach this point, notice M cancels out, but you have to know which M that was, right? It's little m. Big M didn't cancel out. So any calculation I do from now on, I'm going to use big M for. And that's good news. That means that if I put a different satellite with a different mass in the same orbit, it's still going 158. The mass of the satellite doesn't matter if we make this assumption. So a spacewalking astronaut doesn't go flying away from the space station when he leaves because he has a different mass. And so that's good for the astronauts. Now I want to look, I have R. This R is the radius of the circle. That's what it always is. When you use centripetal acceleration, this is always the radius of the circle. What is this R, though? This is the distance between M and M. Which happens to be the same in this problem. But again, when we get rid of this assumption, I'm just kind of dropping a few hints for later. When we drop this assumption, these two things aren't the same value, but they are here. So we simplify, and I can solve for big G. And so big G is V squared times R over big M, right? And so if you put in the values for that, 158 squared times 200 over 500, you get about 10,000. And I'm pretty sure the programmer used 10,000. Whoops, I don't want to zoom in. Used 10,000 when they wrote this code. And so we're going to use 10,000 from now on. If you actually do the work, it's like 9,980 something or whatever. So now that we know what big G is, we can move on here. And what we're going to do is put another satellite in an orbit at a radius of 100. And so that is going down to question 7. So I'm about ready to erase all this stuff. So if you want a copy of it, do a screen capture or use the camera feature on Go to Training. And so this is about ready to go. Ready? I'll give you less warning in the future. So goodbye. It's gone. And so now we want to add a third mass here. And this is one problem with this program. Notice it changed all my work that I had. I have to go back and change this real quick. It really messes up my students when they're doing this lab, but it's in the directions, so they should read those. So now I've got body 2 back to the way it was. And body 3 is 0.001 in mass. I'm going to put it at a radius of 100. And so the question is, what do I put in for the velocity? How fast does it need to go? It's not going to be the same as this guy. And so to do that, we would go through the same process. I'll do it really fast. You draw a free body diagram. That's the force of gravity. That's plus. Sum of the forces equals ma. And you get G mm over r squared equals mv squared over r. We just had all that up there. Little m canceled. One of the r's goes, but now we're solving for v, square root of g, big M over r. And so that is circular orbit speed. And now that we know what big G is, we can solve for that. And so again, we're using just the program units. Distance is pickles. Distance is pixels. Time is frame rate, and mass is just something they kind of made up. And so, so now the radius is 100, and we get 224. So according to this, we want to put 224 for the speed. And so if I say start now, we should have 2 circular orbits. The one that was given to us, the purple one, and the one we just made. So you can make other circular orbits and so on. And so that's one of the basic skills you need on more than one mechanics C test. They give you this equation. I gotta go back to, they give you this equation and they say prove it. And so free body diagram, F equals ma, and you have this on the equation sheet and that on the equation sheet. And so practice makes perfect. Now we're going to do activity 4, where we're going to derive the equation for the period, how much time to go around. And so again, I'm going to erase this, but I think you can, if you got the previous screen, you have this one too. So this is going by, so camera. And so for period, I want to know the time to go around once. And so these things are going constant speed. And we know speed is change in distance over change in time. And if they go around once, the change in distance would be 2 pi r, whatever r is, the radius for this one, let's say. And the change in time we call the period. So I want to solve for the period. Well, we have an equation for v from before. I'm not going to go through all that again, but I can put that in for the velocity and solve for the period. And so the period is 2 pi r over the speed. And so it's 2 pi r over the square root of gm over r. And so that's the equation, but usually you don't leave it like this. And so I have a 2 pi, and I'm going to bring this to the numerator. So I get the square roots of r over gm. All I did was invert this. But I have an r here I'm going to bring inside. So if I bring it inside, I now have r cubed, because I have an r squared times this r. And so this is normally how it's written. And again, that's something they would ask you to prove. They give you this equation, and they'd say, show that that is what the period of a circular orbit is. And again, this is assuming big M is much bigger than little m. In other words, big M isn't moving. It technically is, but it's negligible. And in question 8, they want us to predict the ratio of the 2 periods. So we want the ratio of body 2's period, maybe we can fit this on the same screen, to body 1. And you might just say, oh, body 2, that's the bigger one, or not to body 1, to body 3, sorry. And so body 2 is this guy at a radius of 200. Body 3 is a radius of 100, so it's the blue one. And so notice which one is taking more time to go around. Notice the purple one's slower. We know that from this equation. And it has more distance to go. And then you can look at this equation and see, oh, bigger r, more period. And so if it's twice as much, you might guess what happens to the period. How would that change it if I put in 2r? And so you have the period equation here. And so I have 2 pi, well, let's just do it here. So 2 pi square roots. And so body 2 has a radius of 200 cubed over g, which is 10,000. You don't really have to put the numbers here because they're going to cancel. And then by times big M. Notice it's big M here, right? Because it was big M here. Little m canceled out. And then body 3 is 2 pi square root of 100 cubed over 10,000. That's what g is for this program only. 10,000 times 500. So you can see the g cancels out. I didn't have to write that there. So does big M. And the 2 goes, and the pi goes. And so I end up with the square root of 200 cubed over 100 cubed. And so that ends up with being the square root of 2 cubed, or 2.83. And some people might have just noticed that right away. Hey, if I put a 2 here and cube it, if I double the radius, it's going to go up by square root of 2 cubed, or 2 to the 3 halves, or whatever you want. And so that's a typical multiple choice sort of question. They'll say, how does body 3's period compare to body 2, or body 2 compared to body 3? And you can set it up as a ratio. And they do expect you to know this equation even on the multiple choice. Remember, you don't get an equation sheet on the multiple choice. So that's kind of a review of circular motion, circular orbits. That is everything you need to know about circular orbits. And you do need to know that for the B test as well. You just need to be able to prove this stuff. So let's move on to elliptical orbits. And so this is going to disappear here. So if you are interested in it, take a picture. And again, I am monitoring the chat, so if you have a question, let me know. So here goes. It's gone. And so what I'm going to do is turn this guy into an elliptical orbit. And so I'm going to add velocity. And so what happens if I make it go faster? I got to stop and reset. And so instead of 224, let's make it go 250. I'll stop it here. So notice it went out. It was coming to here, so it went higher up. Does that make sense? I made it go faster and it went up. It's really just like throwing a ball in the air, kind of. You add velocity to a ball, it goes up. Then it falls back down. And so if I add more speed to it, and I know ahead of time what to add here for what I'm trying to do, I want it to reach 400 out here. So I start it, and I think I have the right one. Pretty close, almost right on 400. Notice each grid is 100. So let's let it come back around. And so we are on question 11. Let's skip to that. And we are looking at an elliptical orbit. Notice that the star, the planet, is at one of the foci of it. The other the focus is out here. Nothing's there. That's called the vacant focus. And we give names to these different points. So let's just let this thing run. And this point here is called the periapsis. I spell it right. I left an A out. Periapsis. I can do that better. Let's write bigger. So the closest point is the periapsis. You don't really have to know that name, but usually when they talk about it on the test, they label it point P. And so you know why it's P, it's the closest point. And this furthest point out here is called the apoapsis. If it's around the sun, they call this perihelion, and this aphelion. Around Earth, they call this perigee, apogee, and there are other names for different planets and moons. We won't go into that. Let's just stick with, this is kind of the math term for it, for an ellipse. And if you look on question 11, they want us to label where do we have max velocity. And so if you just watch this guy, when's he going the fastest? Sure looks like here. And we can work that out. If I draw it here, let's say that's where he is, the force of gravity is straight toward big M, right? And his velocity is tangent to the path. And so you can see gravity is putting the brakes on here, right? It's pulling backwards. So this whole part of the orbits, it's slowing down. And you can see that from the simulation. And then if I draw him here, gravity is toward the planets, and the velocity is tangent. That's force of gravity. Let's label that. So you can see now there's a component of the force of gravity in the direction of motion, so it's speeding up all along this half of the orbit. So if it's speeding up, I know right here it starts to slow down. It's going to have maximum velocity. And so we know then over here would be the minimum velocity. And then kinetic energy is just related to the velocity, or really the speed. And so I've got to have maximum kinetic here and minimum kinetic here. What about potential energy? And you might know the potential energy equation, negative G m over r, that we use for orbits. And that makes it kind of tough to see where it's maximum. You say, oh, if I have a small radius, this is a bigger number, but it's a bigger negative number. And so really the maximum is out here where you have the greatest height. And so that still works. Even though MGH doesn't work, the higher up you are, the more gravitational potential you have. And so here I have a minimum. You also might have guessed that because the total energy is a constant. Gravity is a conservative force, and so when you do work against it, that goes into potential energy. And so these two have to add to the total energy. And so if I have minimum kinetic, that means I have the most potential. If I have maximum kinetic, that means I've got the least potential. And these two do add up to the same thing. And so you can use energy to answer questions about elliptical orbits. So the kinetic energy at periapsis plus the potential energy at periapsis would equal the kinetic at apoapsis plus the potential at apoapsis, or any other point. But there's another quantity that actually is easier to work with. Notice with energy we have two kinds, and we got this negative sign. There's another thing we're going to look at here, and that is angular momentum. And so that's one thing good about gravity, is it reviews stuff you had all year long. So notice we had Newton's laws, circular motion, we're getting into energy here, and also angular momentum. And so angular momentum is I omega. And for a particle, which is what we would consider this object, we don't have its dimensions, it is mr squared is what I is. And we saw this earlier, omega v is omega r, so omega is v over r. And maybe you just learned angular momentum to be mrv. There was an angular momentum webinar earlier. And so this is pretty much always what you're going to use for orbiting objects. So my question is, where is this the greatest? If you look down question 11, you're supposed to indicate where is the maximum angular momentum. Well, it's MRV, so it's got to be where it's the fastest, right? So you might say, oh, it's going to go here. But somebody else might say, oh no, it's going to be where you have the biggest R. I think it's going to go over here. Who's right? Kind of hard to say. But remember what changes angular momentum. To change angular momentum, you need a torque. And torque is force times lever arm. So the force would have to be the force of gravity. So look at the satellite here. There's a force on it. But does this force have a torque about the big M, about the axis of rotation? It's parallel to the axis. And this is the component perpendicular to L. It's a cross product, if you know what that means. But really, you want to know this, right? To cause a torque, you need to push perpendicular to the lever arm. This is parallel, so the torque is 0. And if the sum of the torques is 0, angular momentum can't change. And so I also know the angular momentum is constant. And that is easier to deal with than energy. Now, you might end up using energy, so don't forget that. But let's look at one with angular momentum. And so this is question 12. And so this is all going to disappear here. So again, if you're taking notes or you want to do something with it, it is about to go away, and it is going, gone forever. And so let's see if we can figure out how fast it's going here. What is the velocity at apoapsis? Well, we know r apoapsis, and we know v apoapsis. That's what I have down here, right? The 283. And we also know r, if I can draw that straight. Oh, I switched things, didn't I? That's a p. Nobody caught that. You're supposed to send me a message when that happens. So VP is periapsis. Sorry about that. And so this is our apoapsis, and that is 400. How do I know that? 1, 2, 3, 4. If I put the cursor on it when it comes through this point, it'll real briefly tell me that it was 400. See it flash down here. We could pause it and find that out, but it's 400. We can see that from the grid. And so I'm claiming that angular momentum is constant. So that means the angular momentum at periapsis equals the angular momentum at apoapsis. And so M RP VP equals M RA VA. And the mass cancels out. And so VA is RP over RA times VP. And so that's way easier than using the potential and kinetic energy. And in this problem, you got 100 over 400 times 283, and it's about 71. Doesn't it look like it's going a lot slower out here? 1/4 as fast, but we will pause it here. And let's see, escape. And so I'm going to hit stop right when it gets to that point, or as close as I can. And then we'll see what its velocity is, just to check ourselves. Almost there now. And so if I put the cursor on it, it tells me down here, I can't move the cursor, but if you look to the right and down, it says Vx is 0.4 and Vy is negative 70.4. So if you got the magnitude of that, it's about 71, pretty close to it. So don't forget the angular momentum problems tend to be easy if you remember what it is. One important thing to remember about angular momentum for a particle is mRV, but this is only the components perpendicular to r. And so that worked here and here. But somewhere else, you'd have to be given what this component is. Usually they don't have you do that, but just I threw that out there. So let's move on. All these problems so far, we've been making this assumption. And so now we're going to get rid of this assumption and look at what I call a binary star system. And so we are moving to the next activity, activity 6. And so I'm going to set this up to work because I think it's good to have a visual, and then we will see how we came up with these things. So all this is going to disappear here. So again, if you want notes, take a screen capture. Here it's going. And so now we're just going to have two bodies. And body 1 is going to be 400. And I'm going to put it at x equal 40. Oh, that's velocity. X equal 40. And I'm going to give it a velocity of 32. And then body 2, I'm going to make it 100. And I'm going to put it at negative 160. So their total separation is 200, right? Because this guy's at positive 40, negative 160. and I'm going to give him a velocity of, I'm going to have him go in the other direction, negative 126. And so why do I do that? When I hit start, I have them in circular orbits, but is the purple one orbiting the yellow one? Or is the yellow one orbiting the purple one? They're kind of both orbiting something we talked about in a previous webinar, their center of mass. And so I'm going to stop it right there. And so how did I know what numbers to put here? And so with a problem like this, you might be given only the masses. So let's give these guys numbers. And so M1 is 400. You can see it. Well, we're going to assign variables, I guess. And M2 is 100. And so notice I'm not saying big M and little m, even though one is smaller, because they're of considerable size, they're equivalent size, and the force of gravity of M2 is making M1 accelerate. So we are no longer making that other assumption. So this is definitely a mechanics C sort of problem. And the only other thing we're told is that these guys are 200 apart. And so my first job is to figure out what are the radii of the two orbits. What is R1 and R2? And I know that they're measured from the center of mass. And so this is a center of mass problem, at least to start with. How far is the center of mass from the yellow one? Or, and you might try this later, how far is the center of mass from the purple one? See if you can answer that. And so you might remember the center of mass equation. X center of mass was 1 over the total mass, summation, I equal 1 to n of mi xi. How many of you honestly remembered that? Probably none of you. I'm going for my notes here. So no, I think I would have known it, but I've taught it for a long time. And so this does work. 1 over the total mass. So the total mass is 400 plus 100, or 500. And then what does this business mean? Well, n is 2. And so I have up in the numerator, m1, which is 400, times its x position, which I'm measuring from here. And so 0 plus m2, 100 times its position. I'm saying this is x equals 0 and this is the positive side. You could wait till this guy's on the other side if that bothers you. And so it's 100 times 200. And so I get 40. Now, if you don't remember how to do that, there's another way to do it. Pretend that these are two guys playing seesaw. And I want to know what this distance x is. I know the sum of the torques are going to be 0 if they're balanced on the fulcrum where the center of mass is. So the torque on this side has to equal the torque on this side. And so 400 times x, my unknown distance here, has to equal 100 times, I'm not going to call that y because then I get a different unknown. I'm going to call it 200 minus x. And so you get 400x equals 100 times 200, or 20,000 minus 100x. And so you get 500x equals 20,000. Or you get x equals 40. You're more likely to remember this trick than this equation, at least in my opinion. So little center of mass review. So we know R1 is going to be 40. So what is R2? Well, see if you can do this trick to solve for R2. Call this x and see if you can do it. But we know now it's going to come out to 160. And so that's step 1. That's what we have to do in question 12 to set this system up. And notice that's how I set that up. The next step is, how did I figure out how fast they're going? And so that's what we're going to do next. So I'm about to race this. I'll put the answers up here, but it's about ready to go. So if you want to save that, take a capture. Again, if you have any questions, I know we're doing a lot here, send me a chat. So here we go. It's going away. And so let's put our radii back on. So R1 was 40, and so we did a lot of work just to figure that out, right? R2 is 160. Now I want to know, how fast is this guy going, and how fast is this guy going? I didn't do that to scale. We know this one's going slower. Now you can do this with angular speed, and I'll mention that. You might give that a try, but since this is probably the first time you've seen something like this, we'll do linear speed, and that's what the program takes anyway. So what do? We draw a free body diagram of star 1. And we draw and label all the forces acting on it. Hey, I'm getting deja vu. We've done this. Direction of the acceleration toward the center. Newton's second law. Sum of the forces equal ma. And the force is the force of gravity. And this would be m1. So whatever I drew the free body diagram of is the mass here. So that's important. And then that's a centripetal acceleration. So it's going to be v1 squared over r1, right? And the force of gravity, we know, is g m1, m2, the product of the masses, over r squared. And so that's going to go into here. But what is this r? What number would you put for that? And so I'm going to wait a second. You think about, based on what I have here, what number would you put here? Would you put 40? And so this is always the distance between M1 and M2, the two masses, whatever, big M, little m, whatever you call them. And so what's the distance between them? Notice it's always 200. And so this is not R1. I'm going to write it out with symbols. You could put numbers in. It's R1 plus R2 squared. And so this is always the radius of the circle. So you'd put 40 in for that. This is always the distance between them. But in a problem like this, they're not the same. So that's really the key difference between this and what we did before. Notice which mass cancels? M1. And so it's the mass of M2 that dictates how fast M1 is going. That's how they discover planets around other stars. They watch the star wiggle, and they calculate what M2 has to be. And if it's below a certain threshold, about 80 times the mass of Jupiter, they know it's a planet. And so this is how they discover exoplanets. And so if we carry this out and solve for V1, it doesn't simplify that well. You get G M2 R1 over R1 plus R2 squared. And if you put in all the numbers for that, I think it's worth doing here. I won't do it for the other one. Whoops, what am I doing? There's no eraser with this thing. I have to erase everything. What can we do here? Down low here. So V1 is the square root of 10,000. Remember, this program uses G as 10,000. And M2 was 100. And R1 was 40. And then down here, I'm going to write this out so you can see it's 40 plus 160, but you would just put in 200, right? And what does that come out to be? It comes out to be 32. Actually 31.6, but this program makes you round to the nearest integer. Now, if you went through all these steps for M2, I'm not going to do that. I'm going to leave that for you to do. You should be able to show it's going 126. And if you want to check yourself, you might look at this equation. What do you think will be different? Instead of M2, what are you going to have there? What are you going to have here? This would be the same, though. And so I'll leave that as an exercise for you to try later. This has been a free response problem. It's been a multiple choice problem, a really hard multiple choice problem. But that's kind of the difference between this and what you might see on the APB test. So we're going to move on to activity 7. So if you want a capture of this, take one now. I will point out something real quick here. So if you go to my website, go to www.lghs.net, I have more help for this stuff online. And so it is here. And so just go to academics, teachers and staff, and then hit me. And so if you hit gravity, you can see I have some videos, binary star orbits. It goes through another example similar to what we just did. And gravity inside a planet, I'm not sure we're going to get to that today. That's more of a simple harmonic motion thing, but we'll see. So now we're going to set this up differently. Set body 1's mass to 500. And I'm going to put it at -400 in the x. So way off to the side, mainly so we can see what's happening. And then I'm going to make body 2 little again. So we're back to big M, much bigger than little m. And I'm going to put it at -385. So it looks like it's on the surface, right? And how far apart are they? Their centers are 15 apart. That's the key number to know. And then this guy I'm not going to have moving. And this guy I'm going to send him off at not y velocity, x velocity, 775. So I'm going to launch him off this planet or star or whatever it is. And so I hit start. He goes up. Oh, he's coming back down. What goes up must come back down, right? Or does it? What if I make it 800? Is it going to come back now? Oh, it does. I don't know why the whole star blows up when it comes back down. And what about 825? It's not much faster. And I think you'll find if you run this at home, it never comes back. And so what goes up doesn't always have to come back down. And I'll leave that running while we go through. So maybe I'm wrong. Maybe it will come back. And so we're talking about something called escape velocity. And there is an equation for it. We're going to derive and we'll see what escape velocity really is. We know that it's greater than 800, or that's an 8, should be 800. And we'll find out it's bracketed between 800 and 825 if this never comes back. And so it's less than 825. So we'll try and solve for that. Now to drive escape velocity, that's what you really need to be able to do for mechanics C. And so we use energy to do that. And so here when I launch, I have I have kinetic energy and I have gravitational potential. Remember, gravitational potential is negative GMM over R. And so it's not zero on the surface like when you used to do good old MGH. The only place it's zero would be when R is where? At R equals really big, right? Like super big, like infinity. And so that's the only place it's zero. And so that's kind of a weird thing. The way to think about it is look around your room. Everything you see in your room has negative gravitational potential energy. Where did it start at? Well, when the solar system formed, it was really far away in this huge cloud, this called a nebula, right? And somebody or somehow it ended up in your room. Somebody brought it from infinity to your room. And so it's below infinity, it's negative potential, gravitational potential. Just like you could say your ceiling in your room is zero potential, and everything in your room would be negative then. And so if you bring it back to infinity, then it's back to zero. And so what I want to know is how fast, how much kinetic energy do I need to escape? Well, really, escape velocity means the minimum velocity to escape. And so if I have the minimum velocity, I'm going to launch when I reach infinity. I'm going to infinity. What's my velocity when I get there? It's going to be zero. Because if I'm going faster than that, then I went faster than I needed to escape. So how much energy total do I need to escape? Well, I'm going to have how much kinetic when I get there? Zero. I'm going to have how much potential when I get there? Zero. And so that's the key idea with escape velocity. You need a total energy of zero. I know it sounds crazy, but it's actually one of the reasons we set potential energy equal to zero at infinity is because it makes it easier to come up with escape velocity and other things. So we can use conservation of energy to come up with an equation for escape velocity. So the initial energy equals the final. The initial is kinetic. Call it K escape. Just say that's what we're up to. Plus the potential. And the final energy is zero. Well, so is the initial energy. But I have kinetic. I'll let V escape. And I have potential. And again, this minus sign goes with the equation. It's part of the equation. It is given in the equation sheet. And so that adds up to zero. So the little m cancels, so any object is going to have the same escape velocity for whatever planet you're on. And so if I solve for V escape, I get square roots of 2gm over r. Now, is that an equation to memorize? It might come in handy on a multiple choice, but if you can start from this and derive the equation, that might come in handy on a free response. And I am predicting a gravity free response on this year's test. They haven't had one in a long time. They used to come fairly regular. This is my #1 bet for a free response on Mechanics C this year. And something to do with escape velocity certainly would be a high likelihood. Now, I don't know anybody that works at the College Board. I wouldn't bet money on it. But if I had to pick one thing to be ready for, it would be this. And by being tuned into this webinar, you've got a leg up on people. And so what would be V escape for our object here? It's the square root of, well, 2. And remember, G is 10,000 for this program only. And then the mass is the mass of whatever you're escaping from. Notice it's little m that canceled out when we derive this. So being able to derive it keeps you from making mistakes like that. When my students do this, here's where they have trouble. What is r? It's the distance between the two objects, right? And between their centers. And so that is going to be 15. Because one's at 400, one's at 385. And so that comes out to 816.5. And so if you put 816 and wait for a long time, it does come back. But if you put in 817, I've never seen it come back. Maybe I wasn't patient. You have to watch a long time maybe, but it sure seemed to work. And so we are going to move on here. And so if you want the notes on this, take a picture. And so it's going away. And so we're going to move on to activity 8 in the lab. And so we need to reset this. And so I'm going to put 2 objects now. So we're back to same mass objects, and I'm going to put one at negative 50 and one at positive 50. And I'm going to have them go away from each other at 210. I picked, whoops, I went away from each other, so that's going to be negative. And so I picked 210 because they should come real close to leaving the screen. They might, I don't know, on my laptop, they might leave the screen. We'll see. Stretch that out some. And so if I hit go, you might predict what's going to happen, right? They are going away from each other, but they have a mutual pull of gravity. And so they're going to slow down and stop right about there. And then they're going to fall back. What do you think is going to happen when they collide? It's going to blow up. They collide, and then they come absolutely to rest. And that's because if we reset this, what's the initial momentum? So the initial momentum is 500 times 210. But if we make to the right positive, the other one's got negative. Well, let's say plus 500 times negative 210. So that equals 0. And so it sure looked like an inelastic collision. So it makes sense that they stopped. We'll come back to this later. But that isn't what I want to do. I want to predict how far apart are they when they stop. What is our final? How far apart are their centers? And what do we know? We know our initial. That's not 50, right? It's 100. It's the distance between their centers. And we know their masses, and we know energy is conserved. And so we can use conservation of energy to solve for their final separation. And we saw it's something over 400, and we'll see if that works. And so this is called a linear orbit. And so they are moving in straight line. Energy is probably your best bet for analyzing what happens. You might think, oh, wait a minute, it's F equals ma. That would work. Problem is, does the acceleration stay constant? The force changes as they move apart. And so that makes that more difficult. And so we want to use energy. So we say the initial energy equals the final. So what do we have to start with? Well, we definitely have potential energy. And you might say, oh, they both have potential energy. And you're right, they're both sharing potential energy. You can't have gravitational potential energy with just one object. You need both of them. So this term is the initial gravitational potential energy of the whole system. Then I have kinetic energy. Well, which one has kinetic? They both do. And so there are two kinetic energy terms, one gravitational potential energy term. What about at their furthest point? Well, I know at the furthest point, the velocity is 0. So there's no kinetic. There is just gravitational potential energy. Call it UG final. And so I have an equation for gravitational potential energy, negative big G. Let's just call them both big M, right? They're the same thing. And then over our initial. And then I have plus 1/2 big M V squared plus 1/2 big M V squared. Now you sure could just multiply one of these by 2, but be careful. What if they had different velocities? Then you'd have a different problem. Then you'd have to use momentum to solve that. That would make this much harder to do. But the fact that the same mass, same speed, it's still a tough problem. And then the final potential, again, they're sharing the potential energy. It's the potential energy of the system. You're always used to saying, if here's the Earth and I throw a ball up and the ball has MGH up here, and so the ball has all the potential. It's not true. The ball and the Earth share the potential energy. But if the mass of the Earth is much bigger than the mass of the ball, the Earth isn't going to move much, not at all, really, for a ball. But if this object was similar in size to the Earth, then they'd both be moving, and you'd realize, oh, they're sharing the gravitational potential energy. And so we get some simplification here. A big M cancels out. And then we can combine these guys. And so let's simplify it up here. I get, let's see here. We get negative G M over Ri. And then I have a V squared over 2 plus a V squared over 2. So plus V squared. And that equals negative G M over R final. And so we're trying to solve for R final. And so I'm just going to give you what the algebra turns out to be here. We're kind of running low on time. So your job is to solve that for R final. Well, what could we do? We could we could change signs here, right? Can I make that a plus and this a minus and that a plus? That might help you. And so I'm going to put parentheses around this guy. I'm going to swap places between those two. And so our final is GM, that's this term here, divided by this thing in brackets. And if you put in the numbers for that, I don't have room here and I don't want to erase it on you now. You put in the numbers, you get 847. And so that means the total distance is 847. So that'd be 423 each. And so when we run this, when they reach a stop here, they should be at 423. So this will be our, maybe our last. I might do one little thing here, but feel free if you have to go. And so here we go, reset, start. So I'm going to stop it right when they appear to be motionless. There. And so I put the cursor there. That one's at 423. The cursor on there. That one's at 423. And so it worked. Tough problem. You might try and do the reverse of this. What if I told you that they started out this far apart, and I said when they're here, how fast are they going? Well, we know it's 210. Let's see if you could solve for that. Let's see here. And so what if we change body one's mass to 550? What's going to happen now? It's going to change how far apart they get, and that would be a tough problem. You would again have to use momentum. But watch what's going to happen when they hit. Oh, nothing, because I forgot to change this. This program follows the motion with a camera. It follows the center of mass. And so I had to uncheck system centered, which is a mistake my students always make. So now I feel bad. So who had the most momentum? Body one was going in the negative direction. And so most of the momentum was in the negative x. So afterwards, there's some negative x momentum. And I think we're going to stop here. But if you want an extra problem here, it's question 15 on the lab. Solve for V final. And you should come up with 10. And so that's where you want to go back up here to momentum.